Imagine reaching your hand into the path of a rapidly swinging industrial steel arm, knowing with absolute certainty that it will stop precisely 1 millimeter from your skin. For decades, the factory floor was a segregated landscape, divided by heavy steel cages separating fragile human workers from the blind, brutal efficiency of automated machines. Today, those cages are vanishing. A new architecture of production is taking hold, one where flesh and metal do not just occupy the same space, but actively anticipate each other's movements in a seamless, choreographed dance. This transformation is driven by collaborative robots, widely known in the industry as cobots. Unlike traditional industrial behemoths designed to perform repetitive tasks in total isolation, cobots are engineered fundamentally for shared intent. They are a new class of machine, built from the ground up to operate safely alongside human employees in dynamic, unpredictable environments. This is not merely an upgrade in hardware, but a profound shift in the philosophy of human-machine interaction, bridging the gap between digital precision and human adaptability. To understand the magnitude of this shift, consider the historical trajectory of factory automation. For over half a century, the primary goal of industrial robotics was raw, unthinking throughput. Machines were heavy, exceptionally fast, and completely unaware of their surroundings. If a human entered their operational envelope, the result was often catastrophic. The solution was brute force segregation, effectively locking human ingenuity out of the actual assembly process once the machines were switched on. The breakthrough that dismantled those physical barriers relies on an array of sophisticated internal diagnostics, primarily force feedback technology. This system allows a robot to constantly measure the resistance it encounters along its mechanical joints. If a cobot bumps into an unexpected obstacle, like a human arm or a misplaced tool, the force feedback sensors detect the microscopic spike in resistance and instantly halt the machine's movement. It transforms a rigid mechanical arm into a highly sensitive instrument, capable of feeling its way through a crowded workspace. Coupled with these internal diagnostics is a dense network of external safety sensors, including advanced vision systems and laser scanners. These technologies create an invisible, dynamic perimeter around the machine. When a human worker steps into the outer warning zone, the cobot might automatically reduce its speed. If the worker moves closer, entering the critical safety zone, the system pauses entirely. The machine yields to the human, fundamentally rewriting the power dynamic of the modern assembly line. As the industry investigates new frontiers of productivity, researchers at the Massachusetts Institute of Technology conducted extensive studies on human-robot collaboration. They discovered that teams comprising both humans and cobots were significantly more productive than either humans or robots working alone. The synergy is born from complementary strengths. Machines handle the dull, dirty, and dangerous tasks with unwavering precision, while humans provide the complex problem-solving, dexterity, and critical thinking that algorithms still struggle to replicate. But what happens when the very nature of physical labor is redefined by a machine that can anticipate your next move? The implications stretch far beyond mere production metrics and efficiency charts. The integration of cobots requires a profound psychological adjustment for the human workforce. Trusting a machine that possesses enough torque to crush bone requires more than just reading a safety manual. It demands a visceral, experiential learning process. Workers must physically interact with the cobots, bumping into them intentionally, feeling the immediate cessation of force, and internalizing the reality that the machine is designed to protect them. This trust forms the true foundation of the binary bridge. To foster this trust, engineers had to revolutionize how these machines are programmed. Gone are the days when deploying a robot required weeks of complex coding by a specialized technician. Modern cobots utilize intuitive, hand-guiding interfaces. A factory worker with no programming experience can simply grab the robotic arm, physically move it through the desired waypoints of a task, and press a button to record the trajectory. The human physically teaches the machine, transferring embodied knowledge directly into digital memory. This intuitive programming has democratized factory automation, making it accessible to small and medium-sized enterprises that previously could not afford the capital or expertise required for traditional robotics. A local machine shop or a boutique electronics manufacturer can now deploy a cobot in the morning and have it actively assisting on the line by the afternoon. The technology scales down just as effectively as it scales up, leveling the playing field across the global supply chain. Consider the contrast in daily workloads. In an automotive plant, a human worker might be tasked with installing a heavy dashboard component hundreds of times a shift, leading to severe ergonomic strain over a lifetime. When a cobot is introduced, the machine takes on the literal heavy lifting, holding the cumbersome part perfectly in place. The human worker is then freed to perform the intricate wiring and final quality checks. The physical toll is drastically reduced, extending careers and improving overall quality of life, and this is just the beginning of their evolution. The next frontier involves integrating machine learning directly into the cobot's operational matrix. Machine learning, a subset of artificial intelligence where algorithms improve their performance through exposure to data, allows these robots to move beyond simple programmed paths. They are beginning to recognize patterns in human behavior, learning to anticipate when a worker might need a specific tool or when a part is slightly misaligned. By analyzing thousands of hours of shared workspace data through neural networks, complex algorithms modeled after the architecture of the human brain, the cobot can optimize its own movements so it never obstructs the human's natural workflow. If a worker consistently reaches for a bin with their left hand, an advanced cobot will learn to approach from the right, ensuring a seamless, uninterrupted flow of materials. The machine begins to act less like a programmed tool and more like an intuitive apprentice. This level of responsiveness shifts the narrative away from the persistent fear of robotic replacement and toward a reality of workforce augmentation. While automation undoubtedly displaces certain highly repetitive roles, the deployment of collaborative robots generally keeps the human at the center of the value chain. The worker is elevated from a manual laborer to a system manager, overseeing a suite of robotic assistants and intervening only when complex anomalies arise. The real challenge lies in managing the cognitive load of this new role. While physical strain decreases, the mental demands of monitoring multiple semi-autonomous systems simultaneously can be exhausting. Institutions like the Fraunhofer Institute for Industrial Engineering are actively studying this phenomenon, focusing on cognitive ergonomics. Their research suggests that while human-robot teams build better things, the interface must be carefully calibrated to avoid overwhelming the human operator with alerts, data streams, and constant decision-making requests. The communication between flesh and silicon must be as fluid and unobtrusive as the physical movements themselves. To address this, developers are turning to spatial computing and augmented reality. Imagine a factory worker wearing a lightweight visor that overlays the cobot's intended path and current sensory data directly onto their field of vision. Before the robotic arm even moves, a faint digital hologram projects its trajectory, allowing the human to subconsciously adjust their own position. The shared intent is made visible, entirely eliminating the element of surprise. This deep intertwining of human perception and machine intent fosters a unique environment of co-creation. The factory floor becomes a laboratory for continuous improvement. Because the cobots are so easily reprogrammable, workers are empowered to experiment with new assembly techniques on the fly. If a worker devises a slightly faster way to orient a part, they can instantly retrain the cobot to match the new process, driving bottom-up innovation. The economic ripple effects of this agility are profound. By drastically lowering the cost of high-mix, low-volume manufacturing, collaborative robots are playing a pivotal role in the reshoring of industries. Companies that previously outsourced production to chase lower labor costs are finding that a highly skilled domestic workforce, augmented by cobots, can actually produce customized goods faster and more cost-effectively closer to the end consumer. The echoes of those early 20th century visions of automated factories still guide the field, but the execution has fundamentally changed. We have moved away from the concept of a lights-out factory, a dark, entirely automated facility devoid of human presence. Instead, the most advanced manufacturing environments in the world are brightly lit, bustling spaces where human creativity and machine precision amplify one another. This transition, however, necessitates a massive societal commitment to upskilling. The blue-collar worker of tomorrow must possess a hybrid skill set, combining traditional mechanical aptitude with a foundational understanding of robotics, troubleshooting, and digital interfaces. Educational systems and corporate training programs are racing to adapt, recognizing that the true bottleneck to boosting factory production is no longer the technology itself, but the availability of humans trained to collaborate with it. Looking ahead, the scale of this collaboration is poised to expand from one-on-one interactions to complex fleet dynamics. We are moving toward environments where a single human operator might orchestrate a decentralized swarm of mobile cobots. These autonomous units will navigate the factory floor, retrieving materials, passing components to one another, and converging on the human worker only when intricate assembly or quality validation is required. Underpinning this future is the integration of predictive maintenance algorithms. These systems monitor the microscopic vibrations and thermal outputs of the cobots in real time, identifying potential mechanical failures weeks before they occur. By ensuring that the robotic assistants are perpetually reliable, the trust required for close quarters collaboration is maintained. The human never has to second-guess the physical integrity of their mechanical partner. Ultimately, the rise of collaborative robots represents one of the most successful implementations of the human-machine interface to date. It is a tangible manifestation of our evolving digital destiny, proving that the most efficient systems do not exclude humanity, but rather design around its unique capabilities. The rigid boundaries between the biological and the mechanical are dissolving, replaced by a fluid, responsive partnership. As these technologies continue to mature, the definition of what we can build and how we build it will forever change. The factory floor is no longer just a place of automated repetition, it is a collaborative ecosystem. In this intricate dance of sensors, algorithms, and human ingenuity, we find a powerful blueprint for the future. The binary bridge has been built, and across it, we are stepping into an era where human and machine potential are inextricably and beautifully intertwined.